and the others which we called the XTDEFs. Remember, we said that the XTDEFs are those ones, those references which are defined in the current program, but they can be used by other programs. And then the XTREFs are those ones which are currently being used by the current program, but they are not defined in that current program. Okay. Okay, so we saw what we do. We write modification records for those ones. We write modification programs or modification records rather for those instructions which will need relocating. That means those format for instructions where we put zeros. And I hope you remember how we are doing it. Okay. Now, let us go into something else. Let us talk about two-pass assemblers. Two-pass assemblers with the overlay structure. Two-pass assemblers with the overlay structure. Now, you remember, we said that most programs are assembled using two passes. And you remember what is done in each pass. Remember, during pass one, the assembler goes through the whole program while assigning addresses to those variables whose addresses are not known. So the first pass is to assign assign addresses to all the variables which are needed in the program. Okay, now you remember that those variables are stored into what we call the symbol table. So during pass one, the symbol table is being generated because there is no symbol table before you go through the program during pass one. But during pass one, as you scan through the program, that means as you go through the program, from the first statement, maybe up to the last, you go on allocating addresses to those, variables, whose addresses we didn't know. Okay. Sorry, there are some guys here who want to enter. And just a moment, let me see how I can maybe allocate them to someone else. Okay, okay. Now, sorry, we are talking about two-pass assemblers with the overlay structure. And I was reminding you that we said okay, are you there? I'm sorry we are being disturbed by this network. Do you hear me now?
Yes, we can hear you, sir.
Okay, please. Thank you. So I was explaining that previously we saw that in order to assemble a program, always remember that assembling just means translating it to machine language. We need to go through the program 2 times. That's why we said that assembling a program usually uses 2 passes. The first pass is to generate a symbol table. That means we give addresses to every symbol which is being used in the program. Then during the second pass, that's when we do the actual translation. That means translating the program from assembler language to machine language using those 2 tables, the symbol table and then the operation code table. Now, it means in some implementations that you may have 2 subroutines, or you may have 2 functions, because you might start with the main program. Then you get to some point and then you call the first pass. So the first pass runs. When it finishes, then the main program calls the second pass. And then the second pass, which is doing the actual translation, also runs until you get to the end of the program. Now, like you can see, these 2 passes are not all needed in memory at the same time, because as the symbol table is being generated, we don't have need for pass 2. So if you don't have enough memory, or in order to minimize on the amount of memory which you are using, you can first load the pass 1, and maybe you load also the tables which are going to be used in pass 1. So those ones, let me say, could be using, let me say, 50 bytes of memory. So you load those ones into memory, and you will run in the 50 bytes. So when they are finished, you can use the same memory to load the pass 2, the same memory, because now when the pass 2 is running, again, you don't need the pass 1. So it means that each of the passes can run independently, but using the same amount of memory. You don't have to load all of them at the same time. So that is what we mean by overlay structures, which means that one structure overlays the other, which means that when one structure is loaded, or when one structure is running, another one is just waiting. You don't have to load both of them at the same time, because that will be consuming a lot of memory, but unnecessarily. So if programs are designed in such a way that one can run without affecting the other, then they can be loaded in the same, memory, because when one is running, we don't need the other. So you let the first one run first, and then the next one will run in the same memory partitions where the first one was. So that is what we call programs with overlay structures. So here in my notes, I'm saying that most assemblers use 2 passes Of course, we all know that. Most assemblers use the two passes, okay? And we know that some tables and some subroutines, that are used during pass one, they are not needed after the pass is completed. But the others, like the symbol table, those ones we need both. Those ones are needed in both passes, because remember, in the symbol table, during pass one, you are using it, you are building it during pass one. And then pass two, you are reading from it. So the symbol table is needed in both passes, being constructed during the pass one, and then being read from in the pass two, okay? Now I'm saying that since the pass one and the pass two are not needed at the same time, they can occupy the same locations in memory during execution of the assembler, okay? So there we have like a diagram showing that you can have a structure where you have the driver program, okay? So we are looking at this diagram, and I was saying that we have what we call a driver program. That one doesn't leave memory because it is needed to monitor the running of pass one, and it is also needed to monitor the running of pass two. So when pass one is running, that monitor program is there in memory. And when pass two is also running, that driver program is also in memory. So that one doesn't leave memory. Similarly, if there are any tables which are needed by both passes, if there are any tables which are needed by both passes, okay? So those ones will also be in memory at the same time. They will not leave memory if they are being shared by both passes. But the tables and the routines which are not being shared, those ones will be loaded one. Okay. I was saying that tables and the routines which are used by both passes, those ones will not leave memory at any one time. But tables and the routines which are only local to pass one, they will be loaded only when pass one is running. And those tables, when they have finished running, the same memory space where they were loaded can now be loaded in with the pass two tables and the routines. So in such a way, you are minimizing on the total amount of memory which is being used by not loading all passes and the tables at the same time. Someone was saying that he wanted to look at this slide. I don't know if there is anything special. Is there anything special about this slide?
No,
Or we continue?
we continue.
Do we continue?
Yes, sir, let us continue.
Hello?
Yes, sir, let us continue.
Hello, hello?
Yes, sir, let us continue.
Hello?
Yes, sir, we are hearing you.
Nobody is hearing me?
We are hearing you, but it's you who is not hearing us.
Okay, someone is saying that I continue. Very good. Now, that is all about overlay structures. If someone was to ask you, what do we mean by overlay structures? You just have to say that these are structures or programs which are loaded in memory in such a way that you don't load all of them at the same time. So in case they are not all needed at the same time, you load those ones which are needed first, maybe for a particular time, and then the others will be loaded after the first ones are no longer required. So in such a case, you minimize on the total amount of memory being used by having all structures running within the same memory locations. By having structures running within the same memory locations. Okay, so that is what I am explaining here. I'm saying that the root segment is containing a driver program which calls the other two segments. So we have a driver program which monitors, like I said, the other segments. And it also contains the tables which are needed by both passes. Okay, so initially, I was saying that the root segment and the pass one segments are loaded into memory, and then the assembler makes the first pass. At the end of the first pass, then you load the pass two segments, replacing pass one segments. So in such a way, the assembler will use less memory and it will reduce on its memory requirements. Okay, so that is what we mean by overlay structures. Just to mention that they are structures which are designed in such a way that when one is running, another one doesn't have to be loaded in memory at that same time. So when one is running, they will have to wait, and then the others will be loaded in the same space where the first ones were running from. Okay. Now we said that normally we use the two passes when assembling a program. That is what usually happens. Mostly we use the two passes. Now there are some assemblers which are one pass assemblers, which mean that you start from the beginning of the program just in one pass, and by the time you get to the end of the program has already been assembled. So you don't make a two passes. So we sometimes have what we call one pass assemblers. Now, like you know, the reason why sometimes we use the two passes, or why in most cases we use the two passes, is because of those forward references. What we mean that we can't translate instructions before knowing their addresses. because in most cases, like you remember, the variables are usually declared at the bottom of the program. So if the variables are at the bottom of the program, and then you don't know where their addresses are, it means that you can't translate them. You need to know their addresses first, okay? Because the variables they are referring to are in front, they are at the bottom. So when you are talking about the instruction which needs that variable at the top, you don't know where that variable is until you generate its address. So that is what we mean by forward referencing, meaning that you are trying to reference variables which are not yet defined. So you need to make the first pass just to define the variables. Remember here, defining means finding their addresses, and then you make the second pass. So what we are saying there in the first bullet is that the main problem in trying to assemble a program in one pass is what we call forward references, because the operands are often not yet defined. Okay. Now we have got two types of one-pass assemblers. There is one type of assembler, one type of one-pass assembler, which we call the load and go. Load and go method. Okay. Now the load and go method does the two things at the same time. It translates, that means it assembles, translates to machine language, and then at the same time, it also loads the program in memory. So as it translates, it also loads the program. Ordinarily, you would expect to start with the source code. So from the source code, you go to assembling. Then from assembling, you go to loading. Then from loading, you go to linking. And then finally, you execute or run the program. Okay. Now, this type of assembler doesn't do two things. It does two things at the same time. It translates to machine language, and at the same time, it loads what has been translated into memory. So that's why they call it the load and the go. Now, if you are using the load and the go method, it means you will not produce the objective program. Because remember, the objective program is the one which has got the translated instructions. That program which has got the header record, the text records, and so on, that is the objective program. So usually, after translating it to machine language, you will then get the objective program, and then the objective program is the one which will get loaded in memory. But now, if you are using the load and the go method, it means you don't have to generate the objective code, because whatever you translate is what you load. Whatever is translated is what is loaded in memory. Yeah? So no objective program is written for the load and the go method. Okay? So the second method uses the objective program as usual, but we will see how it differs from the others. Okay. Now, in the load and the go method, one thing that you can do is to do a small modification of the program. Remember, we said that in assembler, we usually declare at the bottom. We usually declare the variables at the bottom of the program. But now, if you are going to use only one pass, the program can be modified in such a way that the variables which are going to be used are defined at the top. The variables which you are going to use are defined at the top. So at the top of the program, that's where you have your reserve word, reserve byte, word byte, and so on. So you declare them first. Now, when the time comes to start assembling a program, it is now okay that the variables are already known. So by the time you start executable instructions, the variables are already known. So that's why you put them at the top. Now we will explain this one, I think, in the physical class, because it might be a problem to understand it when I'm not illustrating it like on a whiteboard. So let me reserve this part here, the one pass assemblers. Excuse me. And then we will go through them again when we meet next time. So let us start something different. That is the next chapter, chapter 4, which is loaders and linkers. Okay. Remember, I was explaining the trend which is usually used when you write a program. So when you write a program, you usually start with the source code. Okay. Then the source code is translated to machine language by the assembler. So that is what we call assembling. Now, after generating the machine language and then also generating the object code, then the object code is loaded in memory. Like we are going to see, we will see how the loading is done. Okay. Then the programs are linked, the different programs are linked because, like, again, you remember, we said that at times, one program can call on the other. So if one program is calling on the other, or if it has got variables which are needed, but they are to be obtained from another program, then there is a need to link the two programs. So after loading, you link the program, and then finally you run the program. So the trend is that from source code, it is assembling. Then from assembling, it is loading. Then from loading, it is linking. Then from linking, you run the program, or the program gets executed. So loading is done by the software as called loaders. And the linking is also done by softwares which we call linkers. Okay, so we are going to see the loaders and the linkers briefly. Now loading, if someone asks you what do we mean by loading, I think I have already explained this one. This means bringing the object program into memory for execution. Bringing the object program into memory for execution is what we call loading. And this one is done by the loader. Then relocation, I hope everybody remembers what we mean by relocation. Okay. So relocation is modifying the object program so that it can be loaded at any address different from the address which was originally specified. Okay, so a program can be relocated. That means it may be put in two different memory locations other than those ones which were defined when you were writing it. Then linking, we said this means combining two or more separate objective programs, okay, by using references. So you provide references, which we call the external references, which are needed to do the linking, to link the two together. Remember, we have the XTDEFs and the XTREFs. So, Mr. Katerega, I don't know what you want me to repeat. What do you want me to repeat? I was explaining what we mean by loading, what we mean by relocation, and what we mean by linking. Relocation, we saw this one. We said relocation comes from relocate. When you relocate, it means you are changing like your address. Okay? So we said that at times when you change the address, it means that even the variables are going to change. But since assembling is done before loading, you could find that if you relocate the program, it might read the addresses which are not correct, addresses of the operands which are not correct. So we said that a program, we needed to add there some extra information so that we needed to add there some extra information so that the program can run from any memory location. So you don't have to bother that the addresses are used are no longer valid if you have written a relocatable program. And we said that a relocatable program is that program which has got modification records. So that is a relocatable program, which means that it will run anywhere, irrespective of the addresses which were used when assembling it. Okay? I hope it is clear now. Okay, so how is loading done? Remember, the objective program has got the header record, the text records, and then the end record. So the header record is checked first. You remember what is contained in the header record. The header record contains the name of the program, the beginning address of the program, and then the size of the program. Hello? You are not seeing. Hello?
Sir?
You don't see on my screen?
Excuse me, playing with overlay. Yeah. Yes, we are not seeing the screen you are sharing with us.
Oh, okay, okay.
Yes.
Do you see my screen now?
Yes, we are able to.
Okay, so we are now talking about loaders and the linkers. So on that first screen, I was explaining what we mean by those three terms. Loading is just bringing the objective program into memory so that it can be executed. Relocating is to provide that extra information we need, which will enable the program to run from anywhere, irrespective of the addresses which were used when assembling it. And then linking is combining two or more separate programs so that they can talk to each other, and then they are linked by giving them or by using what we call the external references, which could be xtdefs or xtrefs. Okay. Now, how is loading done? Okay, so loading, when loading is going to be done, that means when a program is going to be loaded in memory, of course, we are using the objective program. And you know that the objective program has the header record first, that is one record. Then it has got the text records, the modification records, and then finally the end record. So you remember the header record contains the name of the program, the beginning address of the program, and then the size of the whole program, how big the program is. So when the program is going to be loaded into memory, the header record is checked first. The header record is checked first. First of all, to verify that you are loading the correct program, because you remember the object program, the header record in the objective program has got the name of the program. So the loader checks first to see whether it is loading the correct program, whether the correct program is the one which is being loaded by reading the name. Then it will also get to know the size of the program, okay? So it needs the size of the program to know whether it will fit into the allocated memory space. So if it doesn't fit into the allocated memory space, then it means that maybe the operating system will find another partition of memory where that particular program will be loaded. So the header record is checked first to verify that the correct program has been presented for loading. And again, to verify whether it will fit into the available memory. So that is the use of the header record of the objective program. Now, after checking the header record, then the text records are read one after the other. Now, as you go through the text records, you go on entering both the data and the data and then the instructions. You remember text records contain the data and the instructions. So from the beginning of the program, you go on putting the instructions and the data into the correct memory locations, okay? So that is what I mean there when I say that as each text record is read, the object code it contains is moved to the indicated address in memory. Remember, every record, every text record has got a beginning address, okay, where you are going to start. So when you read a text record, you find where that address is, and then you go on loading the instructions and the addresses into those particular memory locations. Okay? So when the end record is encountered, the loader jumps to the specified address to begin executing the program. Okay? So when I get to the end record, that means that I have got to the end of the program, then I will go back to the beginning of the program, and this time I will start running the program. Okay? Now, like we saw with the assemblers, we have what we call the machine-dependent loader features and the machine-independent loader features. Now, you remember for assembling machine-dependent features, we had the instruction formats, addressing modes, okay? And then we also looked at relocation. Okay, now for loaders, we also have relocation. as one of the machine-dependent feature, machine-dependent loader feature. Okay, so how is relocation done? Loaders which allow program relocation are called relocating or relative loaders. Okay, that means the loaders which include that information which is required for them to be loaded into the correct memory locations. We call them relocating or relative loaders. Now, there are two methods of indicating relocation as a part of the objective program. We have got two methods. The first method uses modification records. Okay. In just a moment. It seems I might have to refer to a program here, to explain this better. But anyway, maybe one thing you remember that we have for the objective program, we have the header records, we have the text records, and then we have the modification records, and then finally the end records. Okay. Now we are saying that we have got two methods for specifying relocation as part of the objective program. We have got two methods for specifying relocation as part of the program. So the first method is the one where we are using modification records. Okay. Remember modification records, those ones they are applying to all those instructions where you have an address. Remember, those instructions we said are format 4 instructions. So for format 4 instructions, you remember that is the format which talks about addresses. Format 1, you remember there is no operand. Format 2, the operands are registers. Format 3, we have displacement, but it is format 4 which is talking about addresses. So only the format 4 instructions are the ones which we need relocating. Now, if you are talking about a relocating loader, the modification record is written.
Not inconvenience.
Hello? Is there a problem?
Was I talking?
Hello? So we are saying that when you write a modification records, you remember how we write a modification record? A modification record begins with the M, followed by the beginning address, which will need to be modified, then followed by the number of half bytes, okay, for the field which has got the address. Now, this is what happens. For example, there is that first program. I think the program where we were beginning from 0000, you can read backwards and find out. But you remember that program which we are using modification records, there was an instruction which was at address 0006, and an instruction which was at 0013, and an instruction which was at 0026. We said these are the only instructions which we need relocation, which will need the modification records, because they were the format 4 instructions which were talking about addresses. Now, if you write a modification record for that instruction, which is at 0006, for example, you will see in the object code, that modification record, if you can find the first modification record here, okay? So that begins with the M. Remember the address was at 0006. So we say that modification will begin from 0007. So you write M 00007, then the number of half bytes, which you remember we said were 5. And then this time we say plus. What we mean, now we say plus copy. Now copy is the beginning address of the program. So wherever you take the program, you remember if, for example, the program you wrote, if you assumed that it was beginning from address 0000, okay? And then you relocate the program so that this time it begins from address 1000. Now you realize that the instruction which was, let me say, at address 0006, if your initial address is 0000, an instruction which was at address 0006 will now be at address 1006 because it has been relocated. The initial address was 000, but when you relocate it, you find that it is now beginning from 1000. So it means that every instruction will have the beginning address added to it in order to get the correct address. So the beginning address is what we add there. So if the beginning address of copy is 1000, that's what we add. So that originally an instruction which was at 0006 will now be at 1006. So for every modification record, we add the beginning address of the program. So that's why you see there that we add the copy, where copy is the beginning address of the program, which is getting modified. I don't know if that is clear. We are just saying that for relocating loaders, you write modification records again like you did with the relocating assemblers. But this time, after writing the modification record, you add the beginning address because that beginning address will be the one which will be added to every instruction when the program is loaded in memory. Okay, is that clear? So you realize that here we will write only 3 modification records. The one for instruction which is at 0006 will be M 000007. Then the number of half bytes is 05 plus copy. The one which is at 0013 will be M 00014 05 plus copy. The one which is at 0026 will be M 000027 05 plus copy. Okay, so all modification records, all modifications will add the value of the symbol copy, which represent the starting address of the program. Okay, now this method is not suitable for a program which uses absolute addressing. Now, the program we are talking about is like the program, the very first program which we saw for the seek, the simple seek. Remember, for the simple seek, we have only one format, opcode, which is 8 bits. Then we have that other bit number 9, which stands for the addressing mode. And then the remaining 15 bits for the address. So every instruction for the simple SIC has got an address. Every instruction for the simple SIC has an address. Whereas with the XCE, it is only format 4 instructions which talk about an address. So if you are going to use the simple SIC, it means every instruction will need writing a modification record for it, because every instruction involves an address. And we said that whenever you talk about an address, that's when you do what? That's when you add modification records, okay? So it means that for format 1, you will have to write the same number of modification records. So you can imagine if you have got 100 lines of code, it means that you are going to write 100 modification records also, because each instruction will need modifying just because it is mentioning an address. So that's why we are saying that the method of writing modification records is not suitable where you have that absolute addressing, where you are using programs which are only using addresses. It will not be a suitable method, okay? So there is a second method which does not use modification records, but the second method is using what we call relocation bits. The second method uses relocation bits. Now, each bit is associated with a machine language instruction. So if you have 10 machine language instructions, it means that you will have 10 bits. So instead of writing a record, this time you write only a bit. Okay? So you see that is a very good method. So instead of writing a modification record, this time you write just only a bit, either a 1 or a 0. Okay. Now a 1 will represent an instruction which needs modifying, and a 0 will represent an instruction which does not need modifying. Now those 1s and the 0s are written, or they are gathered into an area which we call a bit mask. They are gathered into an area which we call a bit mask, okay? And that mask is represented by 3 hexadecimal digits. Okay. I'm wondering if you can access the very first program that we saw, that very first program which has got which is for the simple SIC. That very first program for the simple SIC. Can you access it now? Is it possible? Hello? Hello? Hello?
Yes, sir, we are hearing you.
So I was asking, is it possible to access this first program? Can you access it so that I can use it to explain? Or we can refer this one also to a physical class. I don't know. Because it might be a bit hard to explain when you don't have that program. Someone is saying that we can refer it to a physical class. Okay, maybe that is what I feel now. If we can agree, I think let us postpone this class because most of the things we are dealing with now might be a bit hard to explain when we are not referring to these programs. So I beg that we postpone this class until next Wednesday when we will be having a physical one where we will complete the one-pass assemblers, which we discussed in chapter 3, and then we will continue with loading and linking, which we are dealing with currently. So I beg that we stop here now. Okay?
Okay, so don't you have anything you could tell us to read before we come to the class?
Come again?
Don't we have any reading before we could come to the class on Wednesday, the physical class on Wednesday?
Okay, maybe I can send the notes for the loaders and the linkers. Didn't I send them? Maybe I didn't. But
we do have them.
you have the loaders and the linkers.
No, we don't. Please
Okay.
send us notes.
Then I will let me send these ones to your class rep, the loaders and the linkers. But for chapter 3, the assemblers, I request that you read just the one-pass assemblers. They have two types. When we meet physically, I will first explain how they work. I think those ones.
Okay.
Okay.
Oh yeah, is there any textbook you recommend us to go and seek more information?
There are some textbooks I recommended at the beginning of the class, gentlemen. Maybe you can refer to if you can find it.
Maybe I could.
Okay, someone is saying that chapter 4 and chapter 5, you already have them, so you can share them. You can share them. Okay, so let us meet next time for the physical class. Okay.
Okay.